Hello, everyone. In this talk, I'll focus on the evaluation of big data systems in edge and cloud environments. More specifically, I will first introduce big data, that what exactly is big data, and then I'll dive into the big data ecosystem and the big data architecture. After that, I'll talk about some of my big data projects. And lastly, I'll end on the future opportunities that exist in the field of big data. So starting with what exactly is big data? So there are different definitions that exist of big data. The most common is about the three V's or the five V's. And what this specify is that um, data that is very huge in volume. That is one characteristic of big data. The second characteristic is that it is very variable data in terms of it has different formats in different forms this data exists. The third one is value, that it is data from which we can extract some valuable insights from it. The fourth one is velocity, that this is data that is generated at a very high velocity or at a very high speed. The fifth one is veracity, which means that there are inconsistencies and uncertainties in data. So if you are having data that has these five characteristics, in that case, we can call it big data. Now, big data is a field that it has evolved and that is still on the rise, that is further evolving. There is so much scope, there is so much potential in this field. Now, if we look at this data and we look at the global big data market, what we see is that it is on a consistent rise. So in terms of $1 billion, what we see in 2025, the market is around $90 billion market. And as projected, it is further going to increase. And when it comes to the domains or the application areas of big data analytics, so it is so pervasive. You can find the applications of big data almost everywhere. For example, you can find its applications in healthcare, in entertainment, in security, in oil and gas, smart cities, and so on and so forth. Now, this is where the important stuff starts in. So when we talk about the ecosystem of big data, and if we look at this slide from the bottom up, so the first thing comes is the resource distribution. So here we talk about the cluster, network, edges, devices, for example, what kind of CPUs, it's a private cloud or is it a public cloud or is it on a single computer? So that is what we talk about in the resource distribution part. Above this is the resource type. So here we talks about the flavors, like for example, in terms of storage, is it in SSD or is it in HDD? In terms of the computing flavors, is it like, for example, a 4-core CPU or is it an 8-core CPU? So that kind of specification of the infrastructure comes in the resource type layer. Above that comes the big data technologies layer. And in this part, we focus on the different sort of frameworks and technologies that exist. For example, in terms of the analysis of data, we talk about Hadoop, Spark, Flink. And then when it comes to, for example, the storage part, so we can talk about Cassandra, MongoDB, Redis, and so on and so forth. And lastly, when we talk about the streaming of data or the messaging systems, in that case, we can talk about Kafka. So there are these, a bunch of technologies that have been created for analyzing large amount of data. Now, in the topmost layer, what we see is the first one is the application area. So as I mentioned that the applications of big data, it is quite vast. The smart cities we are building in oil and gas sector, in entertainment sector, health sector, almost everywhere you would see the applications of big data. Then comes the data generation. So here we talk about, or we focus on, for example, the type of data. So there exist many different types of data. For example, your data could be structured, it could be semi-structured, or it could be unstructured. It could be time series data, images, videos, and so on and so forth. So there are so many different types of data that exist around us. Then comes the source of data. Where from this data is coming? Is it coming, for example, from some kind of sensors like a temperature sensor, or is it coming from some social media, like for example, Twitter data or Facebook data? And similarly, the third one is the access pattern. So is it, for example, something that we access very frequently, like for example, 20 times a day, or is it something that we access, let's say, once a month? Then the lifetime of data, is it placed in hot conditions, or is it placed in the warm category? And what this means is that the organizations, what they do is that data that are to be accessed very frequently, they put it in the hot zone, and data that is not to be accessed very frequently, they put it in the cold zone. So that is how they optimize the cost of data storage. And lastly, about the data processing type, so it is also important that how we process data. Is it something that we collect in batches and then we process those batches, or is it something that the data is a continuous feed and we process it in real time? Lastly comes that how exactly we process this data. So for processing, there are many different kind of techniques. For example, we might apply some optimization algorithms on the data. We might apply some kind of machine learning algorithms like supervised machine learning, unsupervised machine learning. We might apply deep learning on the data. And similarly, we might apply kind of greedy algorithms, adaptive algorithms, and so on and so forth. So there are so many different ways in which we can analyze this data. In a nutshell, the point I'm trying to make here is that there are these different bits and pieces of big data ecosystem, and anybody interested in the big data domain need to understand these bits and pieces before they dive into further details. Now, as far as the more concrete architecture of big data is concerned, so if we look at this figure from the left side, so the first one is the big data analytical frameworks. And those frameworks are used, for example, for batch processing, and they are used for all, as well as there are some for stream processing. Stream processing means that the data is coming in real time and we are analyzing it. The second one is the distributed databases. So as I mentioned that once we process data, then that processed data goes into, for example, databases like Cassandra, MongoDB, Redis, and so on and so forth. And lastly, the third one is about the data ingestion. That how do we feed data into these analytical frameworks? So for example, we might use Kafka to put real-time data into an analytical framework, or we might first store the data and then later on feed it into the analytical framework. So if you look at this figure, down the line, there is an orchestrator that is connecting these different stages, and it starts from the data source at the left. For example, it's a sensor which is generating the data. The data comes either is stored or we directly feed it into the analytical frameworks. After that, it goes into the distributed database, and then at the end, we can sort of do the reporting of the data. So we can perform certain queries on the database and sort of present the data for on interest through a dashboard. Now comes the stages of data. So when we talk about the stages of big data, what it is that we have, the first thing is the big data storage. Okay, the data comes in. The next one is the ingestion. We might directly feed the data from the source, or we might put it first in the database, and then through something like Kafka, we might feed it into a framework, like for example, Hadoop, Spark, and so on. And then when it comes to the third one about the analytics, so in analytics, we have batch analytics, analyzing a bunch of data, or we have stream analytics where we process data in real time. About the application domains, I already mentioned that the use of big data tools and technology is almost pervasive. Every particular field it is touching. And there is a very good saying that data is the new oil, and it applies very much so here as well, that today we are generating the largest amount of data than ever before. And that data certainly needs to be stored, the data needs to be analyzed, and data needs to be sort of the findings or the insights from the data need to be utilized in many different ways. Now, when it comes to our work, so I do want to present around 3 projects in this talk. And what we do is that in our research, we look into these big data analytical frameworks, we look into these big data storage frameworks, and we look at them from many different perspectives. We study them in different kind of cloud environments to sort of see that what works the best. So the technologies that we have explored so far, it includes like Spark, Flink, Hadoop. We use Java or Python programming. Then we use HDFS, Mahout. For machine learning, we use MLlib and so on and so forth. And the key questions that we answer is the first one is, for example, which big data analytical frameworks is efficient in terms of response time and energy consumption? How to automatically configure big data analytical frameworks, and what are the trade-offs involved in the use of big data analytical frameworks. And the reason is that we have different options. For instance, we can go and use Flink, we can use Spark, we can use Hadoop. Which one to use and when to use, that is something we are interested in and we are trying to find out through our research. So if we look at this experimental framework, we use different kind of hardware. Like, for example, we use private cloud like Azure. We use public cloud like Azure. We use private cloud or on OpenStack. We use different kind of Raspberry Pis. And above that, if you look, we use VPNs, we use WireGuard to connect the clouds. And then on the top of that, as I mentioned, that we use different kind of storage, big data storage device technologies, big data processing technology, and so on and so forth. In the way we do our research or the benchmarking we do with workloads like HiBench, Big Data Bench, and YCSP. What exactly we measure in our research, we first looked at the response time, that how much time it takes for these specific tools to process the data. Then we look at the scalability, that when we are increasing the computing capacity, whether the time reduces accordingly or not. We look at the reliability, that whether there are nodes that sort of fail during the processing or not. We look at the energy consumption, and more specifically, we look into the CPU utilization, RAM utilization, disk utilization, and network utilization in these experiments. So the first project is about the performance evaluation of big data analytical frameworks. And in this work, what we did was that we looked at these 3 frameworks like Hadoop, Spark, and Flink. We deployed them on the different clouds like private cloud, public cloud, and hybrid cloud. And then we also did bursting, where we offload the processing from one type of cloud into another kind of cloud under a heavy workload. And we see the impact of those offloadings. So the questions we want to specifically answer here is that what is the impact of cloud bursting on performance of big data analytical frameworks? And more importantly, we looked into the vertical scaling and horizontal scaling. Vertical scaling means that if we have nodes and we want to increase the size of the nodes, like for example, from 2 cores to 4 cores. And then we also look into horizontal scalability, which means that first we have one node, then we added another node, and so on and so forth. And we looked at that whether, the entire system, is it gaining and is it equally gaining from that addition of nodes or not, or addition of cores or not. So this is the setup we had. We had a private cloud, a public cloud, and then we connected them through WireGuard. And then we also had different kind of VMs. These are the workloads that we use, like for example, naive Bayes, script, k-means. And what we found out was that cloud bursting, it degrades the performance of Flink most significantly as compared to Spark and Flink, and Spark and Hadoop. The second one is that in vertical scale-ups, Flink scales better as compared to Spark and Hadoop. Thirdly, that Flink, Spark, and Hadoop, they all scale better horizontally as compared to vertically. So when we are adding more nodes, we get more gain from it as compared to if we are increasing the core size of an individual node. The lessons that we learned from this particular project was that Spark, it is very sensitive to data size. So if we increase the data size, it does impact the performance of Spark more than it does that of Hadoop and Flink. Flink is the winner. It is more user friendly and it is also in terms of performance very good. Hadoop is most consistent. So because we had to run each experiment multiple times so that we can remove the uncertainty. And what we found out was that the results that are given by Hadoop, they are most consistent. Automation is the key when running these experiments in this kind of infrastructure. It is very important to write scripts and then use those scripts to automate the experiment, because here you have to run experiments like thousands of times, and manually doing it takes a lot of time. So automation is something that helps a lot in terms of execution of these experiments. Confirming of version compatibility is important because sometimes when we are mixing all these things like connecting private cloud with the public cloud, running one version of, let's suppose, a big data framework and running another version of big data storage, sometimes they don't work together. So it's important that before running or before installing these technologies, it's important to check that whether the versions are compatible or not. The second project is about the evaluation of the energy evaluation of big data analytical frameworks. And here we wanted to see that which of these frameworks is consuming the least amount of energy. And we looked at these three in the sense that we initially offloaded the computation from an individual laptop to a private cloud, and then we did from an individual laptop to Azure cloud. And we see that, that bursting process, which one is more supportive towards it, like whether it's Hadoop, it's Spark, or it's Flink. The detailed results of this experiment are available in a paper that I'll share at the end. The third project is about the configuration of these big data analytical frameworks. The reason it's important is that there are more than 100 configurable parameters in these frameworks, and they need to be tuned properly in order to make these frameworks work in the best possible way. So for that one, what we did was, like, for example, if we look at this figure, each time we are changing the configuration of the parameter, there is a direct impact on the performance or on the response time. And the same is the case with the scalability. When this tuning, it directly impacts the way the framework scales. So we developed two different approaches. One is called scalar, and it uses a search-based approach to find the optimal value of each parameter. And then another one is adapter, and it uses the rule-based approach to find optimal value of each parameter. And through these approaches, we make sure that these frameworks are tuned in a way that it gives us the most optimal results. As far as the storage technology is concerned, so we looked into different databases like Cassandra, MongoDB, MySQL. And the questions we try to answer here is that when should we offload big data storage tasks to a cloud? Because when we are running on a small compute device, we have to offload to a big compute device when we are under heavy load. Similarly, we looked at that which of these are more energy efficient, and we looked at that whether, for example, they scale better vertically or they scale better horizontally. Now, coming to the future trends as to what we would see most likely in future. And the first thing is the coexistence of public and private clouds. And it's not quite possible for organizations to have all the storage and processing on premise. So under heavy workloads, they have to offload to a public cloud. The second one is that of a kind of a combination of big data and DevOps, because we would need more quicker changes, and in order to deploy those changes, we would need infrastructure for continuous development. The third one is sharper focus on data governance. Now, it is important because what happens is that in future, we will have more and more data generated. Now, it's important that we have governing bodies and rules and regulations as to how that data will be used, and that the privacy and security of data not be compromised. The fourth one is the synchronization of IoT and big data. So we will see more and more use of IoT devices, and then all these IoT devices are likely to generate data. The data will be collected and it will be analyzed for different purposes. The fifth one is user-friendly big data services. So what happens is that one of the learning that we had is that creating that kind of infrastructure, it is quite challenging and it's very technical as well. So what happens is that if you have a large amount of data, but you don't have the technical expertise, you will suffer. And the reason is that establishing that infrastructure is quite tricky. So what is very likely to happen is that big data services will be offered as in kind of service from outside. So as a user, I will not have to go into all the technical bits, but if I have data, I'll be able to extract insight from it. And what happens is that at the moment when we have this large chunk of data, we are able to collect it, but most of it is in a very unclean form. And converting that unclean into a clean form that we can process, it is quite an effort intensive task. So what is likely to happen is that we would have more and more focus on how we can automatically clean the data so that it is of the form that we can automatically analyze. Now, some of the future research questions that we can answer is the first one is that what are the pros and cons of big data services offered by various cloud providers? So, for instance, there are many different cloud providers like Microsoft, Google, Azure, Google, and Amazon. So, it would be very good to do an apple to apple comparison of these platforms or these providers to see that which one is the best under which particular circumstances. The next one is the impact of distance between clouds. So the studies that we did, our private cloud was in Adelaide and our public cloud was in Sydney. But it is quite possible that the public cloud, for example, the private cloud is in Adelaide and the public cloud might be in US. So when we have that larger distance, what is its impact? The next is the distributed databases and its incorporation with integration with the big data storage framework. So for example, whether Cassandra works best with Spark or with Flink. Similarly, MongoDB works best with Hadoop or with Flink. So that would be an interesting question to answer. And lastly, about the streaming engine as well, that for example, Kafka, whether it works best with Flink or it works best with Spark. So that is certainly an experiment that would be worth looking into. These are the publications from which the content has been inspired in. Certainly some of the details of the experiments and the findings that we had, you can find those in these papers. I thank you all for listening to this talk.